Every year, hundreds of oil platforms get installed in the world's oceans. Each one weighs tens of thousands of tons, and at some point, all that weight hangs from a single hook. Not a cable, not a beam, but a hook. A piece of forged steel that looks like a giant fishing hook from another dimension. Around it, the North Sea, a storm, 30-foot waves, a crane swaying on the deck of a ship, and the hook holds. It holds 8,000 tons. That's roughly the weight of 8,000 cars lifted simultaneously above the water's surface. One invisible microcrack half a millimeter wide, and a structure worth billions of euros plunges to the bottom, along with everything attached to it. How do you forge a monster capable of holding 10,000 tons in the middle of a raging ocean from molten steel, at temperatures exceeding 4,000 degrees Fahrenheit? And what critical moment do manufacturers carefully hide from prying eyes? Watch until the end. The answer will surprise you. It all starts with choosing the metal. For giant crane hooks, they use special structural steel where the carbon content doesn't exceed 1%, while chromium additives up to 2% and molybdenum up to 0.5% deliver tensile strength exceeding 145,000 pounds per square inch. These elements aren't chosen randomly. Chromium provides corrosion resistance for marine conditions, and molybdenum prevents brittleness at low temperatures because a hook might operate in the North Sea, where in winter the water barely stays above freezing and the air gets even colder. The raw material arrives as briquettes or ingots weighing 44,000 pounds each. They're loaded into powerful electric arc furnaces with a 440,000-pound capacity. Giant vessels 30 feet tall with graphite electrodes 24 inches in diameter. Steel for these hooks comes primarily from Scandinavia, where it's melted in vacuum furnaces with special composition control at every stage. The logistics are impressive even before production begins. 44,000-pound ingots arrive by barge right to the factory docks. If you're curious how things are made that human lives depend on in the open ocean, subscribe to the channel right now and hit that bell so you don't miss the next episode. When a current of up to 100,000 amps flows between the electrodes and the metal, it creates an arc about 20 inches long that heats the furnace contents to over 3,600 degrees Fahrenheit. This isn't just hot, this is the temperature where steel stops being a solid and transforms into glowing liquid. The furnace slowly rotates for even mixing, while gases are drawn off through powerful filters. The melting process takes 4 to 5 hours, during which the metal is purified through vacuum evaporation and argon purging. The finished melt, a bright yellow color, is poured into ladles lined with fire brick. The temperature at discharge, around 3,000 degrees Fahrenheit. Cranes lift the ladle and transport it to the casting line, where prepared molds are already standing. Massive steel structures weighing up to 200 tons each. The mold geometry is calculated accounting for 2% metal shrinkage. If you don't build in this allowance, the finished blank will come out smaller than required. They pour at a 45-degree angle to avoid air pockets. A stream of liquid metal about 20 inches wide fills the mold in 10 to 15 minutes. Then they seal it with a lid and move it into a controlled cooling zone. And this is where one of the most critical stages of the entire process begins. For the first 24 hours, the temperature drops only to around 1,500 degrees Fahrenheit. The next 2 days, down to 400 degrees. Full cooling to room temperature takes up to a week. Sensors continuously monitor temperature gradients at a depth of 4 inches. The slightest variation can cause thermal stresses that lead to internal cracks, invisible from the outside. During cooling, the metal crystallizes, forming a coarse structure that's later optimized through heat treatment. Workers in protective suits monitor the process through viewing panels, while automated systems record thousands of parameters every minute. The finished blank weighs between 100 and 200 tons, stretches up to 40 feet long, and measures up to 6.5 feet in diameter at the base. Once the lengthy cooling period is complete, the workpiece is pulled from the mold, using cranes rated for 300 tons and transported to the forging shop, a massive facility covering 22,000 square feet with ceilings 80 feet high. Here stand hydraulic presses capable of exerting up to 50,000 tons of force. That's not a typo. 50,000 tons of pressure on a single point. For comparison, the Eiffel Tower weighs about 7,000 tons. These presses push 7 times harder. The workpiece is cut into sections 20 to 26 feet long and reheated in gas furnaces to 2200 degrees Fahrenheit. The metal glows bright red and becomes malleable. Workers in heat suits use magnetic grips to position a section under the press. First stage, rough deformation. The press descends with up to 10,000 tons of force, compressing the metal by 20 to 30% in a single cycle. Each strike lasts seconds, gradually transforming the cylindrical blank into the recognizable silhouette of a hook. Next comes intermediate forging. The metal gets stretched out, they shape cable holes up to 2 feet across and lugs 6 inches thick. The presses are equipped with complex dies made from high-strength steel, matching the exact geometry of the future hook. Total forging cycles: up to 50 per section, with breaks for reheating every 10 to 50 minutes. Between press strikes, they constantly flip and reposition the workpiece. This ensures even densification of the metal throughout the entire volume. Forging doesn't just shape it. It improves the internal structure of the metal, refining the crystalline grain and multiplying the strength compared to the cast state. The final forging stage: precision work on the working section. The main arc of the hook reaches over 3 feet in diameter, wall thickness 12 inches, bend radius 8 feet. The press dies work with accuracy down to a fraction of an inch, forming reinforcement ribs and flanges. After each strike, they blow off the scale with compressed air at 90 pounds per square inch. After forging comes heat treatment, a stage without which the hook would be just a pretty but unreliable hunk of metal. The piece is placed in a furnace for tempering at 1200 degrees Fahrenheit for 20 hours. This relieves the internal stresses built up during forging and gives the metal the necessary impact toughness. Then comes machining on milling equipment. Surfaces are ground to specified roughness. Mounting holes are drilled. Threads are cut into the attachment points. Each hook weighs between 50 and 150 tons depending on load capacity. Manufacturing takes anywhere from 3 to 6 months. The plant produces up to 20 of these units per year, and each one costs millions of euros. They go to crane companies that install oil platforms in the North Sea, the Persian Gulf, and off the coast of West Africa. Now here's where it gets really interesting: ultrasonic testing. This is where manufacturers hide a detail they'd rather not talk about. Every hook gets checked for hidden cracks. Sensors scan the metal with a 5 MHz wave, detecting defects as small as half a millimeter. If even one microcrack shows up, the part gets scrapped. No negotiations, no exceptions. Why is this so critical? Because these hooks work in conditions where failure isn't an option. An offshore crane lifts a platform section weighing 8 to 10,000 tons to a height of 100 to 130 feet above sea level. Waves slam the vessel's hull, the crane sways, the load cycles constantly, slackening slightly, then building again. These cyclic loads are especially dangerous. They make cracks grow even when the overall stress stays within design limits. Under these conditions, a microcrack that slipped past inspection turns into catastrophic failure within weeks. That's why every hook gets tested not once but multiple times. Ultrasound, X-ray, magnetic particle inspection, load tests up to 120% of rated capacity. After passing all inspections, the hook's surface is coated with an epoxy layer 200 microns thick to protect against saltwater corrosion. Then they apply the markings: serial number, steel grade, manufacturing date, and load capacity. This is the hook's passport, which will follow it throughout its entire service life. The global fleet of offshore cranes exceeds 4,000 units, of which around 1,200 are floating vessels with lifting capacities above 5,000 tons. Hook production for them is concentrated in Europe, primarily in the Netherlands, Norway, and Germany. And SN total output across the entire industry comes to just a handful of units per year. The finished hook is loaded onto a specialized platform and shipped to the vessel. There, in the open ocean, they'll attach a cable to it, hook a platform section to that cable, and this piece of forged steel, born from molten scrap, will single-handedly hold the weight of several hundred railroad cars. Waves, wind, rolling seas, and it holds. Because every press strike, every hour in the furnace, and every pass of the ultrasonic probe were done with zero margin for error.
Picture this: 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, zero coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads, the first vehicle in history made from steel with a zero carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal in blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green. The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math. Around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution, and it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane: replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis, powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen. Pure green hydrogen, 0 emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically 0. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks, the first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 Green Steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy, it's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.
Ready to explode with curiosity? In this video, we're throwing open the secret doors to the world of fireworks and firecrackers you never knew existed. Stick with us and you'll see how the magic of the brightest explosions is born from simple gunpowder. Discover the wild history of their creation and learn the unusual secrets of pyrotechnic masters. How do they create explosions in every color of the rainbow from ordinary black powder? Why can a single firework contain over 1,000 pellets, each burning its own unique color? What metals create red, green, and blue fire in the sky? And most importantly, why do masters remove even their wedding rings before work? And how can one stray spark destroy an entire lab? You'll find out how many hours it takes to create one professional firework, which countries produce 90% of the world's pyrotechnics, and what one epic New Year's Eve show costs. This story will make your heart race. Watch until the end, because the most important part is coming. Stay with us until the finale and you'll learn something that will flip your perspective. Don't miss it. Firecrackers. These are the more zippy guys in the pyrotechnic family. Their thing is sound, not spectacle. Even though they're simpler in design, they create the same magic, noise, and adrenaline. Like fireworks, the foundation of firecrackers is black powder, but here everything's a bit simpler. The main goal? Hit the right balance for a powerful bang without the extra special effects. Typically, a firecracker has a powder mixture, a casing, and a fuse. We'll talk about the filling later, but for now, let's learn a bit about the casing. It's a paper or cardboard cylinder that holds everything together. The material needs to be strong enough to contain the explosion until the moment of rupture, but not so strong that it creates dangerous shrapnel. The fuse is the most crucial element. It kicks off the explosive process. This could be a thin cotton cord soaked in chemicals, or more modern ignition mechanisms. The word firecracker comes from the French pétard, meaning explosion. Firecrackers, like fireworks, have Chinese roots. How do they make firecrackers? All components for the gunpowder mixture are carefully weighed and mixed to achieve the perfect consistency. Precision is critical here. Too much potassium nitrate and the explosion becomes uncontrollable. Too little and the firecracker won't ignite. Paper or cardboard tubes are cut to the required length, then filled with the gunpowder mixture. Typically, the casings have sealed ends to create the necessary pressure for detonation. At the top of the firecracker, they create a small opening where the fuse is inserted. It's secured using glue or special putty. The bottom and top edges of the firecracker are tightly sealed, usually with glue or heat sealing. This ensures safe storage and transportation. Next, firecrackers undergo rigorous testing. Manufacturers check sound levels, ignition speed, and blast quality. Not all firecrackers are created equal. Cheap firecrackers often have uneven filling, weak sound, and a higher risk of failure. They use lower quality materials like regular paper instead of cardboard. Quality firecracker casings are made from strong yet lightweight material. The gunpowder mixture is evenly distributed for a consistent effect. Fuses have precise burn times to give users enough time to move to a safe distance. Making firecrackers is no joke. Pyrotechnic factories have strict safety rules. Workers operate in small groups, wear anti-static clothing, and handle minimal amounts of mixture at any given time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question often sparks curiosity. The thing is, a firecracker explosion isn't just a chemical reaction. It's the release of massive energy in a confined space. When gunpowder burns, it releases hot gases that rapidly expand, creating a powerful shockwave. And since a firecracker's casing is tightly packed, that wave is accompanied by the signature bang. Originally, firecrackers were used to scare off evil spirits, and only later did they become a popular form of entertainment. Making fireworks also requires mixing gunpowder with other components first. If gunpowder is the engine of the firework, then the other substances are the artists. They create the explosion of color, light, and shape. To create bright sparks, we need metal powders. That's aluminum, magnesium, titanium shavings. For vivid colors, they use metal salts like strontium, barium, copper, and sodium. Potassium nitrate, perchlorates, and charcoal amp up the explosive energy. After all, they're the oxidizers in fuel. And to hold all the components together, you need binding agents. Water-soluble glues, for example. Each component is first ground down into the finest powder. Imagine gleaming metallic particles dancing in the light as the craftsman preps them for mixing. The powders are so light, it's like they could just hang in the air like magic dust. The most important part begins when the ingredients go into the mill with ceramic or wooden balls. These balls rotate smoothly, grinding the mixture to perfect uniformity. The rustling and gentle tapping create their own rhythm, a sound that reminds you an explosion of colors is being born. When it comes to mixing ingredients by hand, traditional manufacturers approach the stage with reverence. Specialists carefully and slowly mix the ingredients with wooden or copper paddles. Why so slowly? Because even one accidental spark can trigger an explosion. The mixture looks like shimmering sand, where each component has its role. To prevent accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds mysterious alchemy as the gunpowder and dyes form tiny granules. The slightest mistake can lead to tragedy. You know what pyrotechnics masters do before starting work? They remove all metal objects, even rings, to avoid sparks. In many labs, cell phones are strictly banned, and clothing is chosen from anti-static materials. Even the air matters. Facilities maintain controlled humidity so the mixtures don't dry out and become explosive. Before packing the mix into a shell, craftsmen test how it burns. Flame bursts from a tiny sample and everyone in the room holds their breath. Will this be the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors, that's the most exciting part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged, those little pellets packed with special compounds. Where do those brilliant reds, greens, and blues come from? Chemical compounds. For instance, barium creates green, strontium gives you red, and copper produces blue. Once all the components are prepped, the next crucial step is loading the shell, where the heart of the firework comes to life. This is where the explosive mix and colorants transform into a finished product, ready to paint the night sky in every color of the rainbow. The shell is the casing that holds all the fireworks components together. It's made from a special material capable of withstanding high pressure and temperature, yet light enough to soar into the sky. Cylindrical shapes are perfect for creating crisp patterns like rings, chrysanthemums, or peonies. Spherical shapes create symmetrical and three-dimensional effects, like a ball exploding with hundreds of sparks. The process of filling the shell is extremely important, because proper component placement ensures the desired effect. First, they take cylindrical or spherical blanks, usually made from cardboard, plastic, or special paper soaked in fire-resistant substances. The sphere typically consists of two hemispheres that are later joined together. It's crucial that the shell be perfectly airtight. This guarantees the burst happens at the right moment and with the right force. The gunpowder charge, as the main propellant, is positioned in the center of the shell. It's responsible for lifting the firework into the air and detonating it properly. Colorants and specialty mixtures are placed around the charge. Each star element is laid by hand or with specialized machines. Star elements are the pellets that burn in the sky. For spherical shells, these stars are arranged evenly to form a perfect sphere when detonated. In cylindrical shells, charges are often layered or shaped into specific patterns, depending on the intended effect. One standard spherical firework contains an average of 200 to 300 pellets. In large multi-layered shells, there can be over 1,000. To ensure the firework detonates at the right moment, a delay fuse is added to the shell, a small tube filled with a special compound that burns slower. The timer connects to the main charge, providing a delay between the rocket's launch and the explosion in the sky. After all elements are positioned, they're secured with a bonding compound or paper dividers. This is crucial so none of the components shift during launch. The casing is additionally wrapped with strong thread or glue to give it rigidity. Producing a single large professional firework can take up to 4 hours considering the manual assembly and inspection. For a large-scale show with several thousand shells, pyrotechnicians work for several months. The spherical shape is a classic in pyrotechnics. It ensures even distribution of stars during the burst, creating the effect of a perfect circle. Filling such a shell requires even greater skill. Each star is manually positioned around the central charge, and here everything depends on the master. How the components are arranged is how the burst will look. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the gunpowder explodes, the pellets scatter precisely in the shape of the intended pattern. Every year, the world produces over 200,000 tons of fireworks. The production leader is China. It accounts for roughly 90% of global output. For major holidays such as US Independence Day or New Year's in Sydney, up to 10,000 individual fireworks are launched in a single night. This can last over 20 minutes, and the cost of a single show sometimes reaches $5 million.